So in solving exponential and logarithmic equations, the first thing I can always look for is using the one-to-one property. And what that looks like is, first of all, I say I have 2 to the x. Well, let's see if I can rewrite 32 as a power of 2. Well, and obviously in this case I can. So that is 2 to the 5th. And the one-to-one property says, I mean, basically, if anything else is the same, x has to equal 5. So that's my solution. X equals 5. So for the next example, ln of x minus ln 3 equals 0. First thing I'm going to do is kind of set them up to make them look equal. Ln of x equals ln of 3. And then again, by the one-to-one property, x must equal 3. And that's it. X equals 3. In these examples, I want to solve for x. Now, x is stuck in the exponent in both of the cases, so I have to figure out how to get that out of there. So the analogy I'm going to use is, first of all, is if I had a hypothetical equation saying 4x equals 16. Well, we all know we'd solve that by dividing both sides by 4. Now I want you to think, the reason for that is because dividing by 4 is the inverse operation of multiplying by 4, which is kind of keeping x from being by itself. Similarly, if I have sine of x equals 0.5, my only way of getting x by itself is using the inverse sine. And that will take care of the operation using the arc sine of 0.5. So similarly, the inverse operation of e to the x is the natural logarithm, log base e. So I take the natural log of both sides, ln of e to the x equals the natural log of 7. With the rules of exponents, that gives me x ln e equals ln of 7. You'll be able to skip some of these steps as you go further. Natural log of e is 1. So x equals the natural log of 7. In this next one, I have to isolate the variable first. So I say 4e to the 2x equals 5. E to the 2x equals 5 over 4. Now I'm stuck, so I got to use the logarithm. And when I take the natural log of both sides, that's going to give me the natural log of e to the 2x, and again, that's a step you'll be able to skip soon, equals the natural log of 5/4. So I have 2x equals the natural log of 5/4, which I can separate into the natural log of 5 minus the natural log of 4. And now it gives me 2x, so to find x, I just cut everything in half. So x equals the natural log of 5 minus the natural log of 4 all over 2. Now this problem looks really intimidating at first, but once we do a little substitution, recognize you already know how to do this. Now the biggest problem comes because I have two variables stuck in the exponents. And my first trick is noticing a pattern for e to the 2x. And what that pattern is the fact that e to the 2x is actually e to the x squared. So I'm going to use a trick called u substitution. And if I said u, we always write this fancy let u equal e to the x. And now let's rewrite our equation. In that case, I'm going to have u squared, because e to the x is squared as e to the 2x, minus 3u plus 2 equals 0. So if I factor that, I get u minus 2 and u minus 1 equals 0. So u equals 2 or u equals 1. Now, bringing it back to our problem, that just means I can factor this to e to the x minus 2 times e to the x minus 1 equals 0. Now I get two solutions. E to the x can equal 2, or e to the x can equal 1, skipping a step there, obviously. So now, to solve the left-hand one, I say, well, natural log of both sides, natural log of e to the x equals the natural log of 2. So I have x equals the natural log of 2, and that is one of my solutions. My other solution, now, I can just say, use it by the one-to-one property. E to the x is the same as e to the 0, because anything besides 0 to the 0 power is 1, so x would equal 0, and there's my second solution. In these problems, I have a natural log of a variable. So again, I have to use the inverse operation to get that variable out of there. So the inverse of a natural log is, well, an exponent, or in this case, base e. So just by the definition of this, I have e squared equals 3x. Solving for x, I get x equals e squared over 3. And that's all there is to it. This next one I'm going to use the one-to-one property, knowing that I have to have 5x minus 1 equals x plus 7. So, just solving this equation, 4x must equal 8, or x equals 2. Now, it's possible to have extraneous solutions, and when to even look for them will hopefully become obvious from this example. So, if I'm solving this example, the first thing I'm going to look at is, well, let's simplify this. Let's combine them. So, by using the properties of logarithms, I can make this natural log of x minus 2 times 2x minus 3. And on the right-hand side, I can make it the natural log of x squared. And let's put brackets around that so it's clear that all of that is you're taking the natural log of. So, after I multiply that out, I get the natural log of 2x squared minus 7x plus 6 equals the natural log of x squared. Again, by the one-to-one property, 2x squared minus 7x plus 6 has to equal x squared. So, x squared minus 7x plus 6 must equal 0. Factor this, x minus 6 times x minus 1 equals 0. Let's give myself some more room. Then I can have x must equal 6 or x equals 1. And normally I'm all happy, yay, I got my answer. But I need to check them. So I'm going to check 1 in a second here and plug that back in and show you what can be the problem. So over here, I'm going to do my check. When I plug 1 in, I get the natural log of 1 minus 2 plus the natural log of 2 minus 3, and equals 2 natural log of 1. Now, the biggest problem here, right, is I have a natural log of a negative number in 2 cases. 1 would be enough. That's a problem. I cannot have a natural log of a negative number because I can't have a log of any log of a negative number because I can't raise e to any power that would give me a negative number. It's just not possible. So anytime I have a negative number inside a natural log, that's not possible, which means 1 is an extraneous solution. And if you check 6 does work out, and then you realize that x equals 6 is my only solution for this problem. The last thing I'm going to talk about here is the change of base formula, which is useful for evaluating weird base logarithms. Now, in reality, you never see any logarithm that's not base 10 or common log or base e or natural log. But if someone gives it to you, this is how you would evaluate it. So we never actually see this. That's just there to just in general. And what you're going to do is you're always going to relate to a log, a common log, base 10, or a natural log, base e. So according to the formula, to evaluate log base 5 of 17, I simply write log of 17 divided by log of 5. And I just would put that in the calculator. Or I could do natural log of 17 over the natural log of 5. And that would look like this in the calculator, noticing you get the same answer either way. And if I wanted to check my answer, well, I could just type in, again, my base of 5 to the answer, which was the exponent I found, and then notice I get 17, which was my original problem. So I know that this actually works.